Okay, so this is where we left off. And now we're going to talk about probability tree diagrams. So a probability tree diagram is a graphical way that can display prospective cash flows and their respective probabilities that occur at each time period. So basically here you have, let's say this is my first cost because it's happening. Look at this timeline. This is like a cash flow, but instead of having your traditional cash flow with one option for one of these, it is giving you different options. So at year zero, there seems to be only one option. So there's not a lot of uncertainty. Let's say right now you're offering to sell me your stereo for $2,000, right? And there's no nothing's gonna change there. But actually, selling a stereo is a terrible example. Let me see. I'm going to invest $2,000 in this company, whatever. But it is $2,000 because it's happening right now. There's no uncertainty. And I'm being told that I can make up to $750,000 or $750 by the end of the first year through my investment. But there's only a 30% probability of that. There's actually a 40% probability that it'll be $700, and there's another 30% probability that it'll actually be as low as $625. Now, if it turns out that it was $750, then I have probability to make as much as $1,100 by the end of the second year, but as low as $900. And there's a 40% chance associated with this number and a 60% chance associated with this number. If I go for this, if what ends up happening is I make $700, then what's going to happen is I'm going to have either $1,000 or $800, and there's a 50-50 chance. And if I go for the $625, not that I go, it's not a choice I'm making, it's being made for me. But if I end up making the $625, then that means there's an option that it'll be in the second year as high as $825 or as low as $700. So how can we analyze this? This is great and all, but seems a little complicated. So what we're going to do is we are going to, oops, that's not what I want. You know what I want? I need a new slide here. So bear with me. Okay. Okay, we're still all set. Yeah. Sorry, it's being weird, my computer. Okay. Okay, so what I'm going to do is I'm going to make a table. So now my table is going to look like this. So let's see, end of year 0, 1, and 2. I'm going to do the present worth, and then the probability, the joint probability of that, and then the expected present worth. Okay, so now here are my options. I can start, all of them are going to start with this 2,000. So let me try to make this into like a nice little, bear with me. Okay, otherwise it starts going all crooked and then everybody gets confused. All right, so this is gonna be 2,000 and the year 0. 1, 2, 3, 4, 5, 6. I need this to happen. 1, 2, 3, 4, 5, 6. Okay. So then I have two combinations. I'm going to have the following combinations. It can be negative 2,000, 750, and 1,100. That's like my top, most awesome thing that could ever happen. I have this option. I have this one. Basically, I'm going through that graph and seeing what are all the different combinations that I could get. And there's 6, right? And I'm going to go back here in a second just to show you what I'm referring to. So in case it wasn't clear, there's 6 combinations. 1, 2, 3, 4, 5, 6. So it's negative 2,000 for all of them. 2 of them will have this. 2 of them will have this. 2 of them will have this. Okay. Now I can calculate a regular present worth, which will just be, you know, my negative 2,000. Plus some sort of number, P given F, I, what's my I in this problem? 10%, what's my I? It's MR. And then for one period plus this other number, so this is the number from year 1 and from year 2, and this will be P given F, 10%, 2 years. So this present worth gives me the following numbers. Negative 409.1, negative 574.4, negative 537.2, negative 702.5, negative 750, and negative 853. So they all are negative, but at least the first one is clearly the least negative of them. Then if you remember the probabilities, the joint probability that this will happen, let's see, it'll be 0.3 times 0.4, which will give me 0.12. This one, this is the joint probability. 0.3 times 0.6, 0.18. 0.4 times 0.5 will give me 0.2. 0.2. And this one gives me 0.3 times 0.7, 0.21. And the last one is 0.09, 0.3 times 0.3. Now, I'm going to copy those numbers down. 0.12, 0.18, 0.2, 0.2, 0.21, and 0.09. And by the way, make sure that they add up to 1. So those do, and that's great. And now my expected value of my present worth. So what we're going to do is we are going to remember how we did it in the previous problem, is we're going to use all of these probabilities to come up with my expected present worth here. So my expected present worth for each one of these lines separately is going to be negative 49.1, negative 103.4, negative 107.45, negative 140.5, negative 157.5, and 76.8. And if I add all of these, I'm going to get the I'm going to get negative 634.75, which is going to be a good representation of what could help me make this decision. And it's, if you see these numbers, it's sort of an average, but it's a weighted average. Okay, so that's what this whole thing is. The idea here is that we're doing a weighted average. So yeah. Okay. All right. So just remember that times that, we got this, we added it up, and this is the likelihood that each one of these present worths will occur, and we added it and we came to this conclusion. So clearly, again, not a good investment, but that's not the point we're trying to make here. What we're trying to make, the point here is that it's hard to represent anything with these numbers. This is a more representative number. Okay. Excellent. Now let's talk about economic decision trees. Now, I want to clarify, this is a probability tree. A probability tree is not the same as a decision tree. And you're going to see why. Okay, so a decision tree is it's a way of graphically displaying all of the decisions in a complex project and all possible outcomes with their probabilities. So it looks similar, but here's the difference. You're actually going to work your way back and you're going to make decisions. In this one, we did not make any decisions. All we made were calculations that gave us a more representative present worth. In this case, we are going to have decision notes, chance notes, and outcome notes, and we're going to use information provided to make a decision. Oh, we can also use a pruned branch. Okay, so let's look at this example. It says Mistelfic Inc. believes new scheduling software at a cost of $150,000 will allow them to better manage product flow and therefore increase sales. The projection of increased annual sales for the next 5 years and their associated probabilities are below. The following slide shows the decision tree and resulting present worth at a MAR of 75. A MAR of 75. I read this number. A MAR of 12%. So increased annual sales. We think that these are the probabilities, or this is what we were given. 75,000, there's a chance, a 35% chance that will happen. 60,000, there's a 45% chance. 40,000, 15% chance, and 30,000, a 5% chance. So how does this look in a decision tree? Look at this. Basically, in this decision tree, we want to find out, so we have, do we use a current software which has no additional cost and no, you know, nothing, no sales increase? You shouldn't see the prune branch here. That's a little spoiler alert. Or the new software which has a cost of, how much did we say? 150,000. So the extra cost is 150,000. But it'll allow you to increase your sales by these numbers with these probabilities. So what I'm going to do is I'm going to calculate the present worth of each one of these options. And we're going to do it with just your regular negative 150,000 plus 75,000, P given A, 12%, 5 years. And these are going to be the numbers, okay? So that's the present worth I get for each one of these options. So now I'm going to compute right here with these probabilities. I'm going to use this to calculate the expected present worth by doing 120,306 times 0.35 plus 66,288 times 0.45 plus negative 5,808 times 0.15 plus negative 41,000 times 0.05, and this is going to give me 68,992. So that's the number that I have right there. Now, what does this mean? At this point, I'm going to compare this number with 0. And clearly, this number is better, so that's why I prune my branch. And then I bring this back to my decision, which will be a decision of having that kind of a benefit based on my system, because this was positive. Okay? Does that make sense? And some decision trees look different, by the way. Let me show you a different kind. So, Mistofix should purchase the software. The expected present worth of the investment is 68,992. So the present worth of each annual sales increase amount is given in the far right of the tree. And the expected value of the annual sales increase is 218,992, the sum, which is the sum of the probabilities times the respective present worth. If you subtract the initial cost, that yields a net present worth of the 68,000. It's superior to the do nothing option. So it's a decision tree is like a probability tree, but that you have to actually make decisions with. Wow, that was like so deep. Okay, so here we have one more example. This example says a factory building is located in an area subject to occasional flooding by a nearby river. You have been brought in as a consultant to determine whether flood-proofing of the building is economically justified. The alternatives are as follows. A, do nothing. The damage in a modern flow is $10,000 and in a severe flood is $25,000. B, alter the factory building at a cost of $15,000 to withstand moderate flooding without damage and to withstand severe flooding with a $10,000 damage. And alter the factory building at a cost of $20,000 to withstand a severe flood without the damage at all. In any year, the probability of flooding is as follows. There's a 70% chance there's no flooding in the river, a 20% chance there's moderate flooding, and a 10% chance there's severe flooding. If interest is 15% and a 15-year analysis period is used, what do you recommend? So here we are tasked with building our tree. So let's add, this is our decision node, and we have 3 options. Option number 1 is spend $20,000 in alterations. Option 2 is only spend $15,000 in alterations. And option 3 is do nothing. Okay. Okay, so now from here stem our chances. Each one of these will have 3 chances, which are the same ones. There's a chance, there's a 0.1 chance this will cost nothing, because in this particular example with the 20,000, we said that there would be no damage ever again, so that's cool. But in this one, there's a 10% chance will withstand $1,000 worth of damage, and there is a 20% chance of minor damage, which we're covered against, and a 70% chance that there'll also be no flooding whatsoever. And for the third one, where we don't invest, there is a 10% chance of $2,500 worth of damage, a 0.2 chance of $2,000 worth of damage, and a 70% chance of no damage. So what I'm going to do now is I am going, and this alternative right here, is going to, now we're going to do some calculations that are going to help me make some decisions. So basically here we have to do 2,000, because that's the 20,000, the cost of my alterations. A given P, 15% for 15 years. And this gives me a present worth of 3,420. So this is negative. So here, this is going to cost us, or present worth is negative 3,420. This one instead is going to be, let's see, this will be with the do nothing. Oh no, sorry. I'm looking at my notes, which are all messy. So the 1% chance is going of, is it $10,000 or? Oh, sorry. This is gonna. Sorry, I'm trying to read if this is 1,000 or 10,000, but it's no. It should be 1,000. So here we have that. I need to reread the problem. That's what it is. Let's see. Oh, okay. So the 1,000, I got ahead of myself. I see what I did. So it was, this number came from 10% chance of that, of this being 10,000. So it'll be that much. Okay. Now I know what's happening. Sorry about that. To calculate here, what's going to happen is this is going to be 15,000, my cost. A given P, 15%, 15. But this is also going to have a cost, or a potential like damage over here of $1,000. So if I do this, this is going to give me negative, that's a negative, 3,565. I got it. Negative 3,565. So clearly it's worse, because on top of the cost of what I put in the building, there's always this number that came from the 10% probability of that, which we add over here. Okay, so this was minus or plus a negative 1,000, and that's how we got that number. And here for the do nothing, my expected values, this came from 0.2. This is from 0.2 times the 10,000, and this came from the 0.1 times the 25,000 in damages. That's how that came to be. And my expected annual cost is going to be, let's see, just that. So this addition, it doesn't have any cost that we have to spread out, but the cost of this going wrong, the expected cost, is going to be 4,500. So here, negative 4,500, which clearly is the worst of them all. So this is my expected annual damage. So over here, we were calculating expected annual damage. I'm sorry, I just realized that I kind of went all over the place with that one, but it's all good now. As long as you know these are my expected values, and then we calculated these numbers in the bubbles are my EUACs, or, well, my annual worths, in other words. And now I just choose. So in my decision tree, it is clear now that we should choose. So we should prune that one and prune that one, and we should go ahead and invest in the $20,000 alteration, or yeah, $20,000 alteration, in order to avoid all of these potential costs from the floods. Actually, this is a really important and very good application of engineering economics, and risk analysis is trying to decide what the expected potential damage of something is, to then decide whether investing in something, like whether it's insurance or building alterations or any of that, is worth it. So this is a very important part of engineering economics. And we're done. Good job.